play, almost. So let's jump right in and finish off trig functions section 3.3. We've already covered, I'm playing about with this thing, must have knocked it with my hand some time. Right, that's about it. Right. We did most of it last time. The 6 main trig functions, sine, cosine, tans, cosecant, secant, cotangent, and their derivatives. And all I want to do is maybe do some question, or one probably, finding the equation of a tangent line, and then to finish off, we'll do some application questions. So, the first kind, suppose I give you a function, and it is secant x over 1 plus sine x, and I would like to know the equation of the tangent line at x equals pi upon 4, right? So that would be a standard find the equation of a tangent line type question. Well, we know how to find equations of tangent lines. We first have to find the slope and the coordinates of a point. Well, they have told me the x coordinate, which is nice, but I still need to know the y coordinate. So I'm going to have to find the secant of pi upon 2 and 1 plus the sine a. Change that question to that. I just want the numbers to be nice, that's all. So it's find the equation of the tangent line to this function at the sine of pi upon 2 rather than pi upon 4. Pi upon 4 would work, but you get some really ugly looking slope, which I don't want. So we got this fella. Well, if you want to find the secant of pi upon 2, you have to realize it's the same thing as 1 over. I didn't just do that, did I? I did. Third time lucky, I'll make it pi. Should never do questions off the top of your head. There. Now the secant, the cosine of pi is -1, so that guy is -1. There. And the sine of pi is 0. That's so much nicer. Okay, we got an answer. It's -1. So we're really trying to find the equation of a tangent line to this ugly trig function at the point pi, comma, -1. So now we find the slope of the tangent. And we get that by finding the derivative. And in this case, we have an f, and we have a g. So it's going to be a quotient law. And if you differentiate a secant, you get a secant tan. Take away a secant and differentiate that guy. You get cosine. And you get a 1 plus sine on the top squared. And what's that going to get me? Well, I guess I could factor out a secant, do a tan, take away a cosine. That's as pretty as that's going to get.
Professor?
Yes.
I see the f dash, the secant x tan x, but where's the g in that first quantity?
Oh, thank you. And the g should have been squeezed. Aye, aye, aye. I told you I need a holiday. I was very busy yesterday. Secant x tan x. There you go. Times the 1 plus sine x. Take away secant x cosine x all over 1 plus sine x. It's not meant to be as hard as this. Okay, so there's our derivative, I'm going to find our derivative at pi, and we're going to get secant of pi, tan of pi, 1 plus the sine of pi, take away secant of pi, cosine of pi, all over 1 plus sine of pi. Right there, okay. That guy's -1, that guy's 0, that guy's 1, that guy's 0, but that doesn't matter because it's all 0. That guy's -1, and that guy's -1, and that guy's 1 plus 0 squared. So you got 0, 3 lots of negatives, so that's -1 on the top over 1. After all that hard work, the slope was -1. So I have a tangent line with a slope of -1 that passes through the point pi -1. If we call this guy x1, y1, we can then use the point slope equation and we're done. You can check that later. I think that's the answer. So to find the equation of a tangent line, you do what you do every time you're asked that question. You find a derivative, you evaluate the derivative at the x coordinate of the point, and that'll give you the number for the slope. You then take the coordinates of the point you're interested in and put them into the point slope equation. And now we have one last thing to do. Kind of tidy this up, and that is applications. Let me show you the ones that they have in WebAssign. Right, you should be looking at the mass of a spring question. You see that there? Right, so I want you to imagine a spring is like nailed to a wall, and 0 is its equilibrium position. That basically means is if you left the thing alone, that's where it would be, right? It would just rest there. Now you take it and you pull it apart, and then it goes doing, right? Now, if the world was perfect and there was no resistance, theoretically at least, this thing would keep going forever using this formula up here. So the position at time t is simply 8 sine t, which is we would probably call oscillating. So if you're into physics, many things oscillate. And you've been asked to find velocity and acceleration, and then position and velocity and acceleration at that particular time, and then something about what is that object doing. Right, so that's what the whole question looks like. I'll show you a solution now. So imagine, this is a version of question 23. There's your wall, there's your spring, there's the 0 position, there's the thing, and this is called position X. It's a basic copy of what they just gave me. And you're given x of t, which is the position function, at any given time t, and it's 8 sine t. Now, if you want to find the velocity, isn't it the derivative of the position function? So you just differentiate that guy, and you get 8 cosine t. If you want the acceleration, then it's the second derivative, which means you differentiate that guy, and you get -8 sine t. Now, if you find the position, in this case, at 2/3 pi, and then the velocity at 2/3 pi, and lastly, the acceleration at that same time. That's about 2 seconds, very roughly. The position would be 8 times the sine of 2/3 pi. The velocity would be negative, not negative, 8 cosine 2/3 pi. And then acceleration would be negative 8 sine 2/3 pi. Now we try in mathematics, because we prefer exact values, to not type that into the calculator and get 4.123456. We would rather to do an exact value. So some of you may have not thrown away your unit circle. Hopefully you'd remember that that's basically where 1/3 pi is. Isn't that where, whatever, 2/3 pi is, and so on. So we need to find the exact value for that guy. So here's $1 million question. Does anybody know what the exact value of the sine of 2/3 pi is? And later on, the cosine of 2/3 pi.
Negative √3/2? No.
Negative √3/2, √3/2, negative 1/2, or positive at 1/2. Isn't that the 4 choices that you kind of have to play with for 2/3 pi, 1/3 pi, 1/6 pi, 7/6 pi, and all the other guys? Isn't that really the numbers you get? Right. The only ones that you don't need to worry about here are pi upon 4s, because they get you √2/2. Well, let's find out. The sine, oops, make sure I'm in radians, which I am. The sine of 2/3 pi, the sine of 2 pi divided by 3 is 0.866 and a whole load of stuff. Would you agree that that has to be that fella? I can check it for you. The square root of 3 divided by 2. You see? So, if you really got stuck, couldn't you just say, I know it's one of these numbers, and then do it on the calculator, and whichever one appears tells you what it is. So this guy is going to be 8 times √3/2, which gets you 4√3. This guy, show you, cosine of 2 pi divided by 3. This guy gets you the negative 1/2 version. So remember, it's one of these 4. It's always going to be. So you now have negative 4. And this guy is basically that guy, but the negative of him, and you have that. So there's the position, velocity, and acceleration of that spring at the time, roughly 2 seconds. And that's question B. That's question A. And then question, well, don't call it C, but the last part says, in what direction is it moving? And you're saying, well, what do you mean? Well, what they want to know from a drop-down menu is one of 2 choices. Is it moving to the right, or is it moving to the left? Now, only one of these 3 tells you the direction that something is moving. Right? Only one of these 3 tell you the direction that this spring is moving. Is it moving in this way, or is it on its way home? Right? Is it moving to the right? Is it moving to the left? Which one is the only one of these 3 that tells you that? Come on, the physics guys amongst you. Which one? Position, velocity, or acceleration? Which one tells you the direction of movement?
Should be velocity, correct?
Correct. Matthew? Should be, it is. Now this velocity is negative. So going that way, positive, going this way, negative. So the answer is, it's going left. And that was our application. And they have another one that's just uglier, and then you get a video one after that. And so that's the one I've done, but the other two are similar. I think they've got a spring going this way in the second one, and then they go back to a spring going this way in the third one. So, moral of that story is, you have to know your unit circle from time to time, right? You have to know what the sine of pi upon 4 is. Let's move on now to our next topic. And I'm trying to find my thing, and I've lost it. Here we go. We are moving on to a rather big topic, and it is how to differentiate functions using what's called the chain rule. If I had lots of time, I would do tons and tons of examples of the chain rule, because the chain rule allows you to differentiate the most complex situations. Product rule's good, right? Two things are multiplied, you can use it. Quotient rule's good. If two things are divided, you can use them. But the things that they're built from have to be relatively simple, right? The pieces, the two pieces, the f and the g, you know, one of them has to be like e to the x and the other has to be x cubed, right? Right? They can't be too ugly, right? The product and chain rule, quotient rule don't really deal with this. The chain rule allows us to differentiate massively ugly, complex functions. Now, if I asked you to do that by the methods that you know, you're really not got a lot of choices, neither of which are practical. Wouldn't one method be just to foil that thing out? Can you learn? Okay, you got a couple of weeks, William, you could probably do it. Are you going to? No way, right? That would not work. Well, you could say, I could write it as x plus 7, x plus 7, x plus 7 100 times and do a product rule, right? Can you imagine, we know how to do a product rule with 2, we actually know how to do it with 3, but would you agree doing it with 100 isn't going to cut it, right? So you can imagine just what must have happened is mathematicians looking at this function and he's saying, what the heck am I going to do? How am I going to differentiate this guy without spending the next 2 weeks doing some really big, ugly, messy math? And from that motivation, they came up with a rule that allows us to find a shortcut to doing this. And before I tell you how we're going to solve it, we're going to introduce you to a term that gets used a lot. It's going to be called the inside function. Now, the inside function in this situation here is x plus 7. Now, I'm coming back to that guy. I just want to show you some other functions and what the inside function looks like. So suppose I was going to differentiate the sine of x squared plus 2x plus 1. Right? We don't know how to do that right now, but we will. Chain rule will show us. In this case, the inside function is going to be the x squared plus 2x plus 1. Oops. Suppose I was going to do e to the sine x plus 5, right? We don't know how to do that right now, but we will with the chain rule. Anybody want to have a shot at what you think the inside function is going to be when you do that guy?
Just E.
Did you say just E, Matthew?
Mm-hmm.
Right. If it wasn't E, what would your second choice be?
The sine x plus 5.
Okay, that's the right one. Suppose it was, suppose I wanted to differentiate the square root of that ugly thing. What would the inside function be in this case?
EX plus 105x.
Are you getting
So
an
that
idea
was
of,
105.
right? Are we good with this? E of x plus cosine x, right? When we talk about the inside function, it's very often the thing that would be inside the brackets if you wrote a bracket. Now, I wouldn't normally write a bracket there, but if I did, wouldn't it be around these two guys? Definitely have a bracket here. There's definitely a bracket here. So the inside function is, I like the name, right? It's the bit inside the brackets, right? It's the bit that if it was x, wouldn't the question be dead easy? I mean, if this was sine x, or e to the x, or the square root of x, or x to the 100, wouldn't this have been a very easy derivative to calculate, right? But it's not an x, it's a x plus 7, or it's a quadratic, or it's a sine x plus 5, or it's this horrible mess. That's the main difference between easy and ugly. And so let's return back to the original first question. How do you find the derivative of a guy like this? Now, there is a formula for the chain rule, just like there's one for the product and quotient rule, but nobody uses it because it's useless. It's just a theoretical thing. It doesn't help. But if you want to see it, it looks like this. Can you remember composition of functions from 141? Fog and Goth. You can express a chain rule question as a composition of two functions. This guy g of x is actually your inside function. And the chain rule says that it's f dashed g of x times g dashed of x. So that's the formula that nobody uses. It's more a process than a function, than a formula, right? So think the chain rule as more of a process than a function. If you try and use this rule, you'll just get confused later on when we do chain rules inside chain rules with product rules, right? The formula really does, it gets in the way rather than helps. So what I want you to do now is imagine, just for a minute, that the inside function was x. So essentially, aren't you differentiating x to the power of 100? Great. And you treat it as if it was x. So you get 100, the inside function, to the power of 99, times the derivative of the inside function. So in this case, it's 100 x plus 7 to the 99 times, and the derivative of this is actually very simple, isn't it? Just 1. Because I tried to pick the simplest question to start this. There you go. Well, that was simple. wasn't it? The derivative of x plus 7 to the power of 100 is just 100 x plus 7 to the power of 99. Well, of course, they don't stay simple forever, but let's keep them on simple for a little while longer. Let's suppose I wanted to find the sine of x squared plus 7x minus 1. Now, the inside function is this guy, right? So what you're going to get is the cosine of the inside function, followed by the derivative of the inside function. And so if you differentiate the inside function, you get this. And typically, they're not as much in the way of style points in these questions for most of them. You normally write things from simplest to ugliest, and that would be the answer. Suppose I wanted to do an e to the sine x plus x cubed. That's a pretty ugly looking exponential. Are you all comfortable that sine x plus x cubed is the inside function? So you want to differentiate this? It's e to the inside function times the derivative of the inside function. And normally, you put that guy followed by that guy. So you don't have too much in the way of style points. Is that the way you thought that was going to go when I started the question? Huh. But now you've seen it, does it look actually quite reasonable? It's not that weird a rule. Could have been a lot unclear. So let me pick some of these guys that they've got. This is a version of your homework question 1. We have 2x cubed, take away 7x squared plus 7 to the power of 4. This is the inside function. So if you want to differentiate it, it's 4 inside function to the power of 3. Would you agree that's basically the power rule? And then you always finish with times the derivative of the inside function, which in this case is 6x squared, take away 14x. And I'm looking to make this pretty. Right, style points. I don't need to worry about how it looks, but I do need to see if I can do some factoring. I can pull out 2 from here, so that'll be 8. What else can, I can pull out an x from here. So that's going to be 3x take away 7. And I'm just making that look a little bit more together. There's your derivative. So let's try and make things harder. Not all questions are ready to be used. That's a version of question 3. I can't really use the chain rule right now. It's not really written in a format that's going to make it possible for me to do that. I'm pretty sure I know what the inside function is. Isn't it going to be 4x squared minus 7? What I don't like is this 1 over cube root thing. Well, I can take cube roots and rewrite them as fractional powers. So that's a good start. Still don't like it, but it's better. What I'd prefer it to be, wouldn't I prefer it to be negative a third so I can use the power rule along with my chain rule? So this guy has to be first rewritten as a power of to the negative a third. this guy is my inside function. So our derivative is going to be multiplied by the power, inside function, reduce the power by 1, followed by the derivative of the inside function, which is just ax. So far, so good? Right, now, that's not the final answer. I'm going to make it look pretty. So I'm going to do 8 and x and that negative. I'm going to leave that 3 in the bottom, and I'm going to bring this guy downstairs. Right. We've done similar algebra a while back. But the 3 rules of style points are always going to be there. Rule number 1, make it look like the original. Rule number 2 was used here, factor the heck out of it. And rule number 3 is, if it's a trig function, look for an identity that might make it nicer. Well, we don't need to worry about rule number 3, but I do need to worry about rule number 1. Would you agree that the original does not look like that? So this guy has just got one last, I guess, tweak. Cube root, because there's a 3 there. And there's your style points. So if 25 minutes ago I told you we were going to differentiate that, you probably would have freaked out. And would you agree that once you know how to approach it, the chain rule gets you out of all sorts of trouble? Can you see the versatility of the chain rule? Which is why I think it's even more important than the product of the quotient rule. It's because what it allows you to differentiate. I won't do this question, I'll just set it up. How would I rewrite that guy so I could do a chain rule on it?
Parenthesis 3t squared minus 1 close parenthesis to the negative 10.
You nailed it. Now, can you do that with a chain rule? And, multiply by the power and all the good stuff. How about this one? Again, I'm only going to set it up, but not do it. I mean, sometimes you have to prepare things before you can eat them, right? So we have to prepare this function so we can differentiate it, right? Right now, it's not really written in a very helpful format, right? Now, you might say, well, I could make this fraction my inside function, right? I could do that. And can you trust me that it would work, but it would be really horrible, right? The answer would be really ugly. Wouldn't you also have to do a lot of style points at the end with fractions inside other fractions, some being squared and some not? And oh God, trust me, you wouldn't want to do it. It'd be the bottom line. Plus, you'd have to do another chain rule, which is not very good. So let's think of algebra. Algebra can make your life simple, even if you don't always think it is. I want to write this as a different fraction. Any suggestions? Not a clue. We'll go on the bottom.
It'll still be the 5t plus 1, but then you'll cube that.
Would you agree that that's equivalent? It's actually 1 cubed over that guy cubed, but 1 cubes 1. Now that, in turn, would you agree that's much cleaner and easier to differentiate than if you try to, just work with what you'd started with? And that differentiates quite nicely. How about this fella? He's good to go. Our inside function is theta cubed. So the derivative will be the cosine of the inside function times the derivative of the inside function. Yeah. Some questions are just easy, right? Didn't need algebra. Pretty much good to go. That's great. Use it. Now, this one technically is good to go. I'm just going to rewrite it a little bit differently. Now, when I write it like that, is it a lot clearer that cosine theta is the inside function? So I've not really done much in the algebra. I'm just trying to do it to emphasize who the inside function is. So you want to differentiate it. You multiply by the power, and then you reduce the power by 1, right? 15 inside functions squared times the derivative of the inside function. And then you make it look a little bit pretty. And you wouldn't normally leave it that way. You would call it cos squared. And that would be the answer. This is not a chain rule question. This is, can you remember what 5 to the power of x, or 2 to the power of x, whatever, 8 to the power of x, what its derivative is?
Natural log of 5 times 5 to the x.
And in this general version, natural log of e to the x. Now you can imagine you might come across a homework question where that appears and you think, oh, I've forgotten. Wouldn't you go and look for it and find it? And maybe every time you had to go and look for it and find it, won't eventually you just remember it because you don't want to spend all that time of going to look for it to find it, right? So things should just become kind of second nature. And the reason I wrote that one down, oh God, look at that as a weird function. 7 to the power of the square of x. Right? That is one weird function. Actually, it's pretty boring if you draw it. It just looks like that. But it's certainly a weird looking function. In this world, the square root of x, right, is your inside function. Agreed? You know, 5 to the x, 8 to the x, 7 to the x, right? That's the inside function. Which means that I'm going to have to write it. These invisible dotted lines are just for emphasis. I'm going to have to write it as x to the half. Okay, now it's ready to use the chain rule on it. Why did I change the square root of x into the x to the half before I started thinking about chain rule? What's the advantage of doing this?
Makes it easier to do the power rule.
Yeah, because I'm going to, isn't that going to be differentiated in a little while? So I need to know what the derivative of it is. Might as well write it as x to the half right now, so it's ready to be done. So 7 to the power of inside function. You get natural log of 7, 7 to the power of the inverse of the inside function, multiplied by the derivative of the inside function, which is that. Should that be the answer that I write into WebAssign? No. Would you agree it's not like the original, right? Rule number 1. So, natural log is 7. Turn that back into the square root of x. That 2 can come downstairs. Couldn't that be an x to the half, which I'll turn into the square root of x? Are you okay with all the movements in one go rather than me doing it in 2? You see the 2, you see the x to the half, you see that guy, and that guy's always been there. There is your style point, the best way to write theirs. Looking good? The chain rule has the ability to differentiate completely different looking functions. Would you agree that doesn't look much like this guy? Or for that matter, this guy? Yet all of them can be solved using the chain rule, right? All of them can be differentiated. That's the power of the chain rule. And then we add even more layers. We can differentiate that function, but now we have to marry it with one of the other rules that we've got. Would you agree that this is basically a product rule with an ugly bit? So this is going to be my f, and this is going to be my g. So if I wanted to differentiate it, I would use the product rule. What I tend to do with questions that get ugly or just messy like this is I do a little extra working at the side. The function f is the first guy, x cubed, and its derivative, f dashed, is 3x squared. The second function, g, is e to the negative 5x. Do you recognize that that is not a very complicated one, but isn't that still going to be a chain rule question? So when I find its derivative, it's e to the inside function. So it's going to be e to the negative 5x times the derivative of that, which is negative 5. And so the derivative ends up being that guy. Are you comfortable about the derivative of g being this guy? Right, so we did have to use a chain rule along with the product, right? So there are two rules being merged together here. So you differentiate this guy, you get 3x squared, you leave the g alone. You leave the x cubed alone and you differentiate the g, and that gets you negative 5 e to the negative 5x, and your calculus is now finished. And your style points is now about to begin. It looks like the original, but it isn't factored. So give me a common factor from these two terms. And that's basically the first term, and all of this stuff multiplied is the second term. Okay, give me a common factor, one from each.
X squared and e to the power of negative 5x.
You all agree with them? Yeah. Do a bracket. Let's see what's left over. Left over, used up, used up. So there's a 3. There's a negative. There's a 5 left over, and 2 of them being used, but 1's left over. So there you go. I wouldn't really be too worried about that, but I'm a picture straightener, so. Share a little thing with you. I am a picture straightener. If you wonder what a picture straightener is I do not like pictures that are not horizontal. You know, the ones when you put them on the wall and there's like 10 degrees off. It bugs the heck out of me. Actually, I'm looking at 2 of the paint things we've got there, but thankfully they're horizontal, so I'm okay. But when they're not, it annoys me, and I have to go and I have to fix them, right? Because I'll just get bugged. And that's fine in the house, because I'll have, you know, level them up. Unfortunately, under instructions from my wife, I'm not allowed to fix pictures in anybody else's house. So if I come into a house and you open the door and they've got a painting in front of you or whatever it is, and it's 12 degrees off, I've just got to walk by. You ever had to walk by something that bugs you? Like you want to do something, you can't. That's what this is. In math, I have that same kind of whatever it is syndrome. Certain things bug me, and one of them is that this is totally correct mathematically, but for me, this just looks nicer. And so I have to do it even if you don't. To give you another example, mathematically, isn't that totally acceptable? There's nothing wrong with that. It's the correct answer. It just bugs me. It has to be written like that. For me. So if you wonder why I do these things, I may sometimes forget to just say, this bugs me and I'm going to write it that way, but it really doesn't matter at all, right? That is totally acceptable in math. Let's move on and do another product rule. This one is the square root of r, e, r to the 4 plus 5. Would you agree it's a product rule? The two pieces are this guy is going to be f, and this guy here is going to be g. And I'll do my setup as I typically do. That's going to be f. I'm going to have to call it r to the half. I'll now differentiate it. And there's f dashed. The other function g is going to be that guy. This is the inside function, so it's e to the inside function times the derivative of the inside function, which is that guy. Okay. Product rule, f dash g plus f of g dashed. This fella times that guy plus this guy times that fella. Okay, style points. They're that bit plus this bit. Common factor. Can you see anything? Is there anything that this expression and that expression both contain? Common factor.
E r to the 4th plus 5.
Yeah. Now that means I'm going to be left with that guy Well, actually, these two multiply together, don't they? So you add them, you get 3.5. Nobody likes 3.5, so there's 7.5. I'm going to write that again because it's just a little bit messy. I have 1/2 r to the negative 1/2 plus 4r to the 7/2. And I can understand you thinking, well, there's not much I can do. I could call that, r to the half on the bottom and make that 1/2 square root of r. Is that what you were maybe thinking? That this could come downstairs and have a square root? And the answer is no. This is the first time you've probably seen this. There is a common factor. if two terms contain a power of x, or in this case r, there is going to be a common factor. Now, when you have two nice things, isn't the common factor the smaller of the two powers? So in this question here, wouldn't the common factor be x cubed? You all comfortable with the common factor when the things look like that? That's pretty straightforward. When you have fractions, common factors are allowed. And when you have one or both of them as negative fractions, common factors are allowed. So you might say, well, what on earth is the common factor between this guy and that guy? It's the same rule that I used here. It's the smaller of the two. Well, I've got a negative half power and a positive 7 half powers. So the common factor is negative a half. Now, let's see what happens when you use that common factor. This guy gets used up, so you've got a half. We'll go with that. That 4 is still there. Now the hard part. Seven halves take out, or remove, negative a half power from it. What do you get if you take 7 halves and remove negative a half from it? You get 8 halves, don't you? And 8 halves is 4, which means this can now be called that guy, which in turn becomes that guy. So remember this answer that we had? So according to the rules of style points, rule number 2 is factor the heck out of it. Do you see that this expression here could be factored? And it wasn't very pretty, but that's what it factored out to become. And this is considered the correct version, right? The best version of the answer. Now, you might think to yourself, that seems an awful lot of work. What's the benefit? I can tell you a benefit of this one right away. Isn't r equals 0 going to be a bad time for this derivative? Because at r equals 0, isn't this going to be something over 0? And isn't something over 0 going to be undefined? So I can tell you there's either a vertical curve, in other words, the curve does one of these things, or there's a vertical asymptote happening at that point. Now, based on the original function, I don't see any chance of a vertical asymptote. So my best assumption is there's going to be a vertical tangent line to that function. Vertical tangent lines are bad news in lots of situations. Can you imagine this function represented something that was a physical property of a shape? You do not want to calculate it at a point where it's got a vertical derivative. Couldn't that basically blow your electric circuit to bits? Because you'd have an infinite, rate of change, which would be voltage if you were talking about current. You would have bad things happen. Don't you want to know where the bad places are? Just so you can make sure that you don't go anywhere near them. And for math purposes, we like style points. The good news is that that's not a very common question, right? You'll get 3 or 4, but you won't get all of them. So let's move to another situation. And what shall I go? Let's do 15. And question 15, we have a g to the z, 1 take away 3z squared, and the square root of z squared plus 1. You agree it's another product rule? And each of these two functions, that's this one, is going to be a general. Our inside function is that guy. So derivative 2 times the inside function to the power of 1, followed by the derivative of the inside function. And so I get negative 6, 1 minus 3z. Done. The g is the square root of z squared plus 1. Well, I know I need to call that half power. Now I can do the chain rule, and this is going to be my inside function. So it's going to be 1/2 that guy to the power of negative a half, 1/2 inside function to the negative a half, times the derivative of the inside function, which is 2z, and that guy times that guy, boom, boom, and we get z squared plus 1 to the negative. So the derivative is f dash g plus f of g dashed. This guy is negative 6, 1 minus 3z times g, which is z squared plus 1 to the half, plus 1 minus 3z squared times this guy, which is z squared plus 1 to negative a half. Do you notice that I didn't leave them as square roots? I left them as half and minus half powers. So now we're going to have to do style points. I got this guy, and I got this guy. Well, I know that this guy and this guy share a 1 minus 3z, so that's something. I know that there's a z squared plus 1 in here, and there's a z squared plus 1 here. So I'm going to choose negative 1/2, and that's my common factors. Yeah, let's do this one first. There's a z left over and one of these left over. So there's going to be a z 1 minus 3z. And that guy's used up. There's a negative 6. And I have this guy, a half power, remove a negative a half power. Right, a half, take away negative a half. Oh, wait a minute, doesn't that just get you 1? And so you get z squared plus 1. Right? There's that algebra trick again. So I have this fella, and these two guys. So I might as well distribute the 6 and distribute the z. This guy can come downstairs. And that, I hope, gets me negative 9 plus a z, take away a 6. And I just noticed one more thing to finish with. I'm going to be back in a second. Oops, hi, Dizzy. Come here. Come here. It's okay. No. Come here. I'm going to introduce you to the new baby. Well, she's not that new now, but she was scratching on the door. I know, because she wanted in. So this is Chloe. Chloe is a pain in the butt. Chloe loves shoes and magazines and anything that is chewable, including my door. So if I didn't let her in, she'd be chewing on it by now. And doesn't she look cute? Right? So, yeah. Kiss. Thank you. Nothing to do with maths, of course, but she was bugging me. So now that I've said hi to her, she'll probably go and bug my wife instead. How we good? How we doing? Are we good on these generals? Right. Looking at the time, yeah, we've got a few more shots to do. Let me show you an easy one and then a horrible one, because the questions kind of come in and out. So as you're doing this homework, you're going to end up doing a really horrible question that takes, a lot of algebra and a lot of stuff, and then you get this one. I don't need to change this one bit. Agreed? Is it pretty clear that the inside function is tan theta? So you want to differentiate this. You get e to the power of the inside function times the derivative of tan theta, which we all know is secant squared theta. Technically, although it's not much, secant squared is considered a little bit simpler than the other one. That was it. Nothing else to do. And then you get this guy. Oh, okay, this is version of 19, just like 2 questions later. Now, the temptation is to call this fraction the inside function. I'll give you a piece of advice. Try to avoid doing that unless there's no way out, right? Unless you can't figure something else to do. I do not like fractions as an inside function, because won't I have to differentiate that function, which means aren't I going to have to do a quotient rule? And would you agree quotient rules for these guys would be really scary with the other things that are going on? And it certainly doesn't help when it comes to the style points. So we need to find a different way of writing that fraction. And earlier today we did do something that did that. How could I rewrite this? It's still going to be a fraction, I guess, but how could I rewrite it?
But you distribute the power of 8 to both the top and the bottom.
Agreed. Now, right now, I could do that as a quotient rule, right? Nothing wrong with it. It's a nice rule. I could rewrite it like that, can I, and do it as a product rule. Agreed? They're both equally good or equally bad. So, I mean, pick the one you like. I'm going to do a quotient rule, because we haven't done one yet, right? We haven't done a chain rule that had a quotient rule in it, so let's do that one. So, I have this situation. So the top function is going to be this guy. So its derivative, well, if you think of this as your inside function, it's going to be 8 inside function to the power of 7, followed by the derivative of the inside function. And when you tidy that up, you get 24 u squared, u cubed take away 3 to the power of 7, and that's that one. Now, g is very similar. The inside function is that guy. So its derivative is 8 inside function to the power of 7 times the derivative of the inside function. And that tidies up to 24 u squared u cubed plus 3 to the 7th. Everyone looking good? Right. Now I'm going to do the derivative down here because I think I'm going to need a lot of room. F dash g take away f of g dashed all over g squared. I got this guy. So that's 24 u squared u cubed take away 3 to the power of 7 times the untouched bottom. Take away the untouched top times this guy. And the whole thing is over that guy squared. Well, squaring is really the same thing as doubling the power, so you just get 16. Okay, style points. Let's factor the heck out of this. Right, that's your first expression, that's your second expression. Give me any common factor you can see, and there's a lot to pick from here.
24u squared.
Agreed. Okay, what power of u cubed minus 3 can I get out of both of them? Because they both contain it, but they contain a different amount of it. Look at this one, look at this one. What power of u cubed minus 3 can I take out?
7.
Would you agree there's also a u cubed plus 3? And what power can I take out of these?
Also 7.
Would you turn it in space? I didn't realise I'd written that. Would you agree that there is a lot of common factors there? So hopefully it should tidy up reasonably nice. Wish that wasn't there, so I'll kind of stick it up here. Used up, used up, used up. One of them left. So there's a u cubed plus 3. Right. Take away. Used up, used up, used up one of these guys. And the reason I put that minus there is, do you notice that you're subtracting both those terms? So what do you get? You end up with u cubed take away u cubed gone, 3 take away -3, and you get 6. Can you see how you could easily not do the right subtraction and think the answer was 0? And that would have not been correct. I'm putting in a lot of lines here, probably more than you would ever use. Okay, that 6 and that 24 are both numbers, so I should just multiply them together. And that gets me 144. That u squared isn't going to go anywhere. That u cubed take away 3 to the 7 isn't going to go anywhere. But would you agree that this guy and this guy can interact? So I have a u cubed plus 3, 7 and a u cubed plus 3, 16. When they interact, don't you get left with 9? So that's quite a nice, well factored answer. Are we good? Right. Now, this next fella, he's not going to be very nice. This guy is If not the worst one I've shown you today, it's certainly in the top 3. I think it's the worst. But sometimes that's a matter of taste. There is no pretty way to do this question. No matter how we approach this question, you are going to get caught up with some really ugly algebra. I could, for instance, make that entire fraction my inside function. And at least that would make the process easy to say. Wouldn't it just be something to the power of half, and then I could do it? But because that's a fraction, wouldn't the derivative of the inside function be a bit ugly? And that would work. And it's probably just as much work as the way I'm going to do it. Again, I'm doing every line I can think of. I hope you would recognize that turning square roots into half powers is a good start. And that splitting fractions into their pieces is very often a good way to go. And I could leave that guy as a quotient rule, or I could turn that guy into a product rule. Neither of them are going to be pretty, because there is no pretty version of this question. Which one do you want me to do? Do you want me to do a product rule or a quotient rule? I'm going to get the same answer, so it don't matter to me. But which one do you want?
Quotient.
Quotient is it? So according to quotient, this is going to be F, this is going to be G. So F is going to be 1 plus the sine of t to the power of half, and its derivative then is 1 plus sine of t to the negative a half times the derivative of the inside function, which is cosine t, and I'll leave it like that. G is 1 plus cosine t to the half. The inside function for this guy is this one, so it's going to be 1/2 1 plus cosine t to the negative a half, and the derivative of that is negative sine t, and I'll leave that alone. Then move on to here. Since we're doing the quotient rule, it's going to be f dashed g take away f of g dashed over g squared. The derivative of f is this ugly expression times g, which is this guy. And there's no way in the world I'm going to squeeze that in here, so take away, leave the first function alone, times the derivative of g, all over that guy squared. That's the only bit that's actually nice, because if you square that guy, don't you just get a single 1 plus cosine t? So what we are looking at here is the derivative is finished, right? There's no more differentiation to do. Most of these questions are all algebra, making them look good. So top expression is that guy, right? Second expression is that guy. Oh, while I'm at it, won't those two negatives make the answer a plus? So I can forget about signs now. Look at the first expression. Look at the second expression. Can you see any common factors? Because there are quite a few. Tell me a common factor. Something that's in this, something that's in that.
1 plus sine t.
Okay, there's a 1 plus sine t. We'll worry about how much in a minute. Would you agree there's a half? And would you agree that there's a 1 plus cosine t? Again, we'll decide how much of each of those there are. Right, a half and a half, that's easy. Right, there's a negative a half power of 1 plus sine t, and there's a positive a half power of 1 plus sine t, right? You've got that guy or that guy. Which power of 1 plus sine t do we use as a common factor?
The negative 1/2.
The negative 1/2. And can we say that you also use negative 1/2 for the other term? And don't write this down. I've just realized I don't have enough room. So I'm going to have to squeeze it over even further. I'm not doing anything different here. I'm just trying to give myself some more room. Okay, so half used up. Cosine t left over. There's a half power. Take away a negative a half power. A half power, take away negative a half, gives you a plus 1, so you get a 1 plus cosine t. Plus, used up. Remember, they cancel, so I've got sine t left over. And this guy, take away negative a half power, gets you a 1 plus sine t. And so I have 1/2, 1 plus sine t to the negative a half, 1 plus cosine t to the negative a half. Distribute this guy and you get cosine t plus cos squared t. This guy gets you sine t plus sine squared t. And the whole thing is still over a 1 plus cosine t. You didn't think when you signed up for this class that you signed up for ugly algebra class, did you? But there's a lot of algebra in Calc 1. Actually, a lot less in Calc 2. I don't know if that made you feel better, but there's definitely a lot in Calc 1. Still got some style points. Is there anything you can see in here that might simplify? Cos t plus cos squared plus sine t plus sine squared.
Cosine squared plus sine squared is 1.
So I'm going to get out of that piece there a cosine t plus a sine t plus a 1. You can put them in the order, that doesn't matter. Now, a half becomes a 2 on the bottom. Agreed? A negative power on the top becomes the same thing, but positive on the bottom. So that 1 plus sine t, the negative a half, becomes 1 plus sine t to the positive a half. And I don't know why that's there, it should be further over now. This negative a half comes downstairs. Oh, there's already one of these. So you've got 1.5, which we will call 3/2. And after all that work, you might say, please, are we finished? Almost. One more thing to do. Once you've factored the heck out of it, shouldn't you make it look like the original? And didn't the original have square roots in it? So this guy becomes the square root of 1 plus sine t. And this guy becomes the square root of 1 plus cosine t cubed. Now that's what I call one ugly derivative. If I changed it into a product rule, can you trust me, it would be just as ugly, right? You'd end up with the same answer, but it would just be really ugly. So let's take you to a new place. Let's do a chain rule that isn't with a product rule and it isn't with a quotient rule, but a chain rule with a chain rule. And you might think, what does that look like? Let's show you one. The cosine of e to the power of x cubed. Now, if I asked you to differentiate that, wouldn't the inside function be e to the x cubed? Great. So the derivative is differentiate a cosine, so negative the sine of the inside function times the derivative of, the inside function. Isn't the inside function itself a chain rule? Now, how do you differentiate the inside function? Well, you call it e to the x cubed, so x cubed is its inside function. So you have negative the sine of e to the x cubed times the derivative of this guy, which is e to the inside function, times the derivative of the inside function. So you get x cubed becomes 3x squared. And then you make it look pretty. There's something elegant about that. It's a bit like unpeeling an onion. What's a better analogy? Do you know those little Russian dolls that have little Russian dolls inside little Russian dolls? Do you know those kind of things? Isn't that question a little bit like that? There's a chain rule inside a chain rule. This one is not one of my questions. I stole it from Elizabeth Briggs. E to the power of 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 x. You got 1 minute. Differentiate that guy. Have a shot at it. There's your first clue, if you need a clue. That's your first inside function. There's an elegance to this answer if you did it correctly. Okay, here goes. E to this guy. You get the original 1, 2, 3, 4e fella. And then you differentiate this guy, which gets you a 3e fella. Then you differentiate this guy, and you get a 2e guy, and then you differentiate this one. Did you get that nice little pattern? I like it. It's a Russian doll question, right? A chain rule inside a chain rule. Let's show you. Wow, I just used up a whole lot of paper today. Right, let's do a trig version of that. We'll make this our last question. So this is question similar to question 25. And it's a function f of t, and it's a tangent of a secant of a cosine. So there is our inside function. Now, if I asked you to differentiate a tangent, wouldn't you get a secant squared? So if I ask you to differentiate the tangent of this inside function, you should get a secant squared of the inside function, followed by the derivative of the inside function, right? So times the derivative of this now. What's the derivative of a secant? Derivative of a secant. Last chance. There are 6 trigs, that's one of them. What's the secant?
Secant times tan.
That's the one, secant times tan. So we are going to do a secant times a tan of this inside function. So we are going to, oh God, I'm going to write it over here. So we're going to have to do, all right, a secant tan, right, of this guy here, right? So it's going to be a secant tan of the cosine guy, followed by the derivative of the cosine guy. So that's negative sine t. So to make it look pretty, I have a negative sine t first. Then I have a secant of a cosine t, followed by the tan of a cosine t, followed by a secant squared of a secant cosine t. And that is one weird looking guy. I guess the only saving grace is you don't need to do any common factors, right? And you don't really need to look for any trig identities because there aren't any. So we're finished. So last name and bye-bye.